Thank you.
Hi, good morning, sir. Our meeting will start 9:30. So, sir, please wait for us. Okay, sir.
ഹലോ രാജേഷ് സാറേ.
Hello? Hello?
Yes, yes. Okay, sir. Okay, fine.
Is it okay? Is it
Okay,
okay?
okay, sir. Fine. Thank you.
Hello? Have you already begun the program?
No, sir. No, sir. No, sir.
Okay,
Just only started by 9:30 only, sir.
okay, right.
Okay.
Hello everyone, the conference will begin shortly. I also request everyone to mute their audios. Thank you. A hearty good morning to one and all. Today we are all here to be a part of International Conference on Productive Mathematical Discourse conducted by the Department of Mathematics, Christnagar College in association with the Kerala Mathematical Association. The very aim of this program is to instill an insight into the modern technological development around the world and to promote students to pioneer new paths in the field of mathematics. With the blessings of Almighty, let's begin the program. First of all, I request Dr. Mary Metilla Rose, Head of the Department of Mathematics, Christnagar College, to deliver the welcome speech. Ma'am, please.
Ma'am, please unmute your audio, ma'am.
Can you hear?
Yes, ma'am. Okay.
Okay. Very good morning to one and all. Distinguished chief guest, our CMA manager, respected principal, my colleagues, and all participants. It is my great privilege to deliver welcome speech today. First, I extend my hearty thanks to our beloved ICM manager, Father Dr. Tito Varghese, who granted the permission to organize this three-day international conference. I am extremely happy to welcome you, Father. Our principal, Dr. Joel Jacob, whose motivation only made us to organize such conference. I am very happy to welcome you, ma'am. Dr. Sandy Kuriakos, former principal, Vesalios Paulos Catholicos College, Piravam, now Dean PISAT, and Secretary Kerala Mathematical Association, who is an eminent guide, good speaker, and an excellent professor. Sir, it is my pleasant duty to welcome you. Mr. Hari Ram, Cloud Solutions, Aviatrix Marble Studio, California, USA, is our chief guest who accepted to deliver a talk on an initiation of mathematics into technology. We feel honored in offering you a cheerful welcome. Dr. K.P. Uma, a good guide and efficient professor and head of Department of Mathematics, Hindustan College of Engineering and Technology, Coimbatore, who accepted our invitation and is ready to deliver a talk on mathematical model on manpower recruitment. I extend hearty welcome to you, ma'am. I am happy to welcome Mr. Benny George, Head of Department of Physics of our college. Our former faculty, Dr. Esther Jayanti LS, who is now working at Head of Department of Maths, PRDS College, Tiruvalla. She only planned this program from 3 months. I express my sincere thanks and welcome her also for this conference. I welcome each and everyone present here on behalf of Christnagar College. Thank you, one and all.
Thank you, ma'am. Now I humbly invite Dr. Sunny Kuriakos, Secretary, Kerala Mathematical Association, to deliver the inaugural address. Sir, please.
Can you hear me?
Yes, sir. Yes, sir. Okay, fine. Thank you.
Good morning, one and all. Respected Father Toto Varghese, Principal Dr. Jacob, the conveners of this 3 days international conference, respected resource persons, delegates from across the world, and dear friends. At the very outset, let me congratulate the Department of Mathematics of Christnagar College, Trivandrum, for organizing this 3 days international conference. I'm extremely happy to see that this conference is being conducted in association with the Kerala Mathematical Association. At this time, I recall the help and support being rendered by our President, Dr. T. Thiruvikraman. Dear friends, we are passing through a time of utmost distress and chaos. The entire world is told by the COVID-19 pandemic, which is affecting each one of us. But I especially congratulate the department for taking up as a challenge and conducting this program in the online mode. Dear friends, this particular conference is on productive mathematical discourse. Under the domain of this particular area, this domain, there are umpteen number of branches or areas that one could discuss. I'm happy seeing that some of the talks are aiming at data science, then management, resource management, etc. Dear friends, as I told you, this is being organized by the department as well as joining with the KMA, Kerala Mathematical Association. I should say a few words regarding the KMA. As you know, the Kerala Mathematical Association is the only association, professional body in Kerala, which is committed to popularizing mathematical studies. It has its inception in 1962. Ever since its inception, KMA has been rendering services, academic support to many researchers as well as institutions. And also, KMA is instrumental in teaching mathematics, especially newly introduced subjects in colleges, to our teaching fraternity. There are a huge number of members in KMA, both from Kerala and outside. Now, this pandemic has stopped us, prevented us from conducting programs offline. But you know, we exist. I will quote a quotation by Henry Bergson. It goes like this: to exist is to change is to mature, and to mature is to create oneself endlessly. So we should not be deterred by the constraints and challenges. We have to move forward. Always there will be changes occurring, and we are simply existing to change the present condition. And our aim is to mature ourselves and to create endlessly. My dear friends, this international conference definitely will give a platform to all the researchers across the world for knowing new things, how the subject mathematics is being applied in various realms of studies and knowledge. And also, it will give an insight to the recent trends and developments happening in the area of mathematics. Mathematics is always considered as a hard nut to crack. But my dear friends, once we know the logic of mathematics, it is no longer a magic. Therefore, in order to know the logic of what we do and to know the applications that what we do will be definitely exposed by the expert talks and technical sessions planned in this 3 days conference. I especially congratulate the head of the department, Dr. Mechilda, and also the organizing team for venturing into this type of program. And I especially convey my best regards on behalf of the Kerala Mathematical Association to the successful conduct of this 3 days conference. With all your permission and your blessings, Father, we need your blessings and support. I declare this 3 days international conference inaugurated and opened. Thank you so much. And I request all the delegates, please see that this type of conduct of seminars will give us a lot of opportunities. We can continue our interactions through online, and eventually this particular conference is expected to create new research areas and to find out new research problems and solutions, so that our life on this planet, whatever happened, no matter what we are facing now, but I give an optimistic suggestion that we will overcome all these such difficulties and we will come out with solid solutions and help our society to grow better and better. Wish you all the best. I wish all the best to the college as well as the department. Thank you so much.
Thank you, sir. Now I request Mr. Hariram, Senior Cloud Assistant, Aviatrix Marvel Studios, California, USA, to take over the session. Over to you, sir.
Hi, thank you very much. Can you hear me okay?
Yes, sir. Yes, sir. We can hear you.
Okay, fantastic. Well, thank you, Mr. Sunny Kurikos and Mrs. Jaya, who's an assistant professor at CNC, and everyone at CNC for inviting me. It's my pleasure to be here as your first speaker and kind of introduce mathematics and its application in technology. Let me go into some details. I work in computer networking. That's the field that I work in. So a lot of the content that I'm going to discuss is going to be around cloud networking or computer networking in general. But I try to touch on how mathematics is so very basic, and the whole concept of computer networking was born out of mathematics, and without mathematics, there couldn't be the innovation that's happened in computer networking and how essential it is. So clearly a lot of these concepts, a lot of these theories, mathematical theories, apply in a lot of different fields. I know we have speakers from a variety of fields like marine biology. We have people talking about data science and plenty of other places even, you know, so let's go dive in. A little bit about me. I was born Hariram Sankaran in Chennai, Tamil Nadu. I grew up there for the longest time, and I am a science major in high school. I love science, and I also liked, you know, to sports and arts. But like most kids in the 90s and 2000s in India, I was very keen to make a name for myself, and so science seemed like the perfect course of action. You know, physics and mathematics were definitely two subjects that I loved. And I, you know, did my science major. My parents really wanted me to be either an engineer or doctor, typical scenarios, right? I preferred engineering, so I took electronics and communication of engineering as an undergraduate. I actually went to Hindustan College of Engineering in Chennai. I know one of our speakers is from the Coimbatore branch, so it's nice to meet you as well. And then in my course, as I did electronics and communication, I loved electronics part of it, but my interests lie in communication more and more. Mathematics in general applies either way, but the applications in the communication fields was more interesting to me. How you can build circuits to build communication equipment, and how you can get people to talk to each other, communicate, whether it's analog or digital communications. Those are the things that attracted me. And then maybe as a natural fit in the last semester in my undergrad, I took telecommunications, which was study about things like internet and other things that is used for you know, telecommuting, right? You know, people in different places talking to each other. How can you communicate? How can you create those networks that can help you communicate? It just seemed like a natural process, given that I was interested in mathematics and physics and things like that. And then, so in 2004, I took the leap once I finished my undergrad to move to the US. I got a seat in George Mason University in Virginia to do my master's in telecommunications. And when I joined, there was a lot of good courses, around networking and computer networking. That's how I got really sucked into computer networking in general, right? But I had the opportunity actually to teach statistics to over 100 plus students every semester for nearly 3 to 4 semesters. As a master's student, you get to teach the undergrad students that come. That's kind of a job that you do to make some money and pay your fees, all of that. At the time, it just seemed like something I was doing to pay my bills, but reflecting back, teaching statistics and mathematics in general to 100 plus students was really what I think was the best time of my time in college doing my master's. So it was very interactive. I always thought if you can teach somebody how to do something, what you're teaching, right? You might think you know something, but if you can teach somebody the same thing, that's when you really know what you know. So I learned a lot, teaching statistics to these students. And then I got hired as an intern as I finished my, my master's. I joined Sprint to become a network and security engineer. Since then, I've been pretty much in all of computer networking combined with security, right? I work for Sprint. They're like a communication company that does wireless communications. Like Airtel is an example I can think of. I don't know if they're in Kerala, but so that's an example. So they like them. They were building internet backbone where people can communicate and over cell phones and things like that. So I was doing that for the majority of my life there. And then I joined the vendor space, meaning people were selling network equipment and for the computer networking space. That company is called Juniper Networks. A lot of you may have heard Cisco. Some people worked at Cisco, they left and joined Juniper Networks, started Juniper Networks. That's how Juniper started. And then I worked at Walt Disney Studios as an enterprise architect, working on, designing and standardizing and implementing solutions in computer networking for Disney Studios. And then I really wanted to get some level of startup experience. So I became a cloud specialist and as a cloud networking specialist, if you will, at Aviatrix. By startup, I mean they're not a public company or they're kind of a private company, but they have customers and they're catered to a lot of customers. I'll address cloud computing, cloud networking briefly as I go along in the talk, but it's kind of where the future of cloud computing in general is. And mathematics is kind of key to get us there as well. And we'll touch on that. I always love physics and mathematics. I mentioned this earlier. I'm sure as a lot of you have gone through, you've had to memorize log tables. That was not fun. I never liked log tables, but surprisingly, it does come in handy in your real life when you start, applying that to whatever it is that you do. And we'll see examples of how I've been using logarithmic data to represent and calculate numbers and things like that. And on a personal note, I always like ending my introduction on a personal note. I'm married and I have a 2-year-old son. When I'm not working or doing all the responsible things, I enjoy, spending time and being silly with my 2-year-old son. Okay, enough about me. Disclaimer, I am not a mathematics major, as I just mentioned. So I had to do a little bit of research to kind of express myself in mathematical terms. I may even get one or two terms wrong. I'm sorry if I do, but for the most part, I hope this becomes very helpful for you as you continue your journey in the field of mathematics. The entire content here is based on my view, my interpretation of what I think computer networking is and how mathematics can apply to that field, right? If I took some notes from the internet, I did call it out with a star. So anything else is my content and it's just my interpretation. And I'm hoping that it's helpful. Okay. Before we even go into computer networking, right? The idea is mathematics is a fundamental language, right? It is kind of like physics. It is, it's like the language itself. It's fundamental. You know, things are built on top of that. There are a lot of applications. Technology is just one. Even in other fields, not just technology, there's a lot of applications to mathematics. And in technology, there's computer networking, but why should you care about computer networking, right? I like to set expectations and why you think this might connect with you. You know, whatever you learned in mathematics, maybe you will take that and apply in computer networking. Why is this even relevant, right? Well, internet is the all too important thing for all of us, right? I can bet that many of you have one or more than two devices that connects to the internet. You have a cell phone, you have a computer, you have a tablet, you probably have maybe a fridge at home that can talk to the internet. Those things have become possible these days. You know, all of that is because of the advancements in computer networking that's really enabled all of us to be connected like we are. Me being here in the US and talking to folks in India over Zoom is a great example, right? And then what Mr. Sunny Kuriko has mentioned, this pandemic situation has really tested all our mettle, right? Are we going to survive this? Are we going to continue to do our jobs? Are we going to continue to do these learnings, right? Are we going to continue to collaborate? Are we going to continue to exchange ideas? Thanks to computer networking and internet and things like that, it is possible, right? I work from home now pretty much every day, and I still continue to do my work. It's possible because of computer networking, right? And also, even though computer networking is born out of globalization, born out of mathematics, but when you think about global scale, it enables other mathematicians to talk to each other, collaborate over the internet, right? So that's why I think computer networking is a very important field in technology. As such, technology, it has changed lives. It has complicated to a certain extent, but for the most part, it's added a lot of value, right? And computer networking certainly has done the same. It is also a lot of fun, and you know, I've gone through the different phases. I've been a student, I've been a son, I've been a student, I've you know, I've been in the corporate world for nearly 15 to 20 years now and worked. I'm also a father now. So you know, you've gone through different phases, and then you finally come to know that you actually enjoy what you do. Otherwise, you wouldn't be doing this, you know, 8 hours a day for 5 days a week, 52 weeks in a year. You know, so it is actually fun. It's not, you know, not something that you just have to do. It can be a lot of fun, and especially if you're really looking to apply mathematics in a real life or in an industry that can take advantage of all the learnings from mathematics and apply it and to make it better, computer networking is certainly a great place. And we'll see some examples on why I say that, right? Okay. we've set the table. I think computer networking is important and mathematics is very relevant. Let's look at see how what computer networking is in the first place, and then we'll see how mathematics applies, and then I'll close with some thoughts. Okay, so what is a network? Before I go define computer networking, I'll have to define what a network is, right? Let's start with the mathematical definition, right? If you think about mathematical theories about graph theories and network theories that come out of that, it's a simple definition. It's a set of vertices that's connected by edges or links, right? But the definition can be a lot more to it. There could be a lot more things that you can describe about a network, but in general, it's the connection of vertices or nodes, and those connections are called the edges or links, right? Now take that same concept into technology. There's a lot of different types of technology, and network can mean multiple different things even within technology, but we'll touch on a couple. There's analog networking, right? If you think to the past, these days all of us pretty much have cell phones, but in the past we all had home phones, and those operated on an analog basis, on analog data, right? And so you still had to network those things. You still had a switchboard that connected two people. You establish a circuit. Somebody manually did that, and then we improved that and it did it automatically. But it's still, at the end of the day, you still had to connect the two people that were trying to talk to each other, right? And so there's the people, it's the vertices, and then you connect them with these wires, and voila, you now have analog networking, right? Then came the advent of digital networking, right? Digital networking really set, technology to go exponentially, grow exponentially, right? Because now suddenly things were a lot faster, a lot more efficient, a lot quicker, right? And that's when also computers came in, right? So with digital networking, now it becomes computer networking, right? So if you apply that mathematical definition to computer networking, it's basically connecting computers with either physical cables or wireless links. Now, I'm sure a lot of you are used to wireless networking. You have wireless at home for your internet connection, or maybe you have wired connections. So the computers could be connected with physical cables or wireless links, right? You can even connect your printer if you have one at home, a fax machine, you have one at home. Even TVs these days, these are all, in a sense, a computer that is connecting to something else with a physical cable or a wireless link, right? That's your computer networking computers, right? At the end of the day, they all facilitate communication. You want to print something, you connect a computer to your printer and you print it, right? Now, that's in general networking and technology, but networking can be in several areas, right? And mathematics is part of pretty much a lot of that. So for example, a study of your brain's neural network, right? There are still mathematical equations that go in the back end that help you understand how the human brain works, right? How the neural networks are set up. Let's think about transportation. How do the roads connect? Same thing, roads connect people from one place to another, right? There is a lot of mathematical analysis. There are engineers who work on how you can improve traffic, how you can reduce congestion. So even with transport networking, like roads and train tracks and all of that, think about flying, right? People are able to travel to multiple parts of the world because airplanes exist, but airplanes don't exist in a vacuum. They are all flying up there, but there are people controlling it. They're able to look at maps because they have data that's been mapped, all coming from mathematical equations, right? Even think about simple things like social networking. Now that's also, in a sense, networking, right? Your circle of influence, right? You make one friend, now suddenly that friend has 10 friends, you may now have 11 friends, right? You kind of grow your network exponentially. So again, networking can be in several different fields, but we're going to specifically talk about computer networking next. Okay, what is computer networking? In general, we already kind of touched on this, two computers connected, right? But when you start talking about things at scale, now what I mean by at scale is, I'm here and talking to a lot of you over there. It's global scale. How does my computer talk to your computer, right? When you start thinking about things like that, that's where technology really helps, right? And then also all the inventions, the discoveries that's gone along with it, because of fundamental languages like mathematics and physics, we were able to create computer networking. Some things that we will go straight into right after this are like, how does networking work? What are the different layers? And at each layer, I'll touch on how mathematics is relevant. The different types of equipments like hubs or switches, routers. Routers are one of the most important parts of networking when it comes to computer networking. And we'll see why, right? When you just have hubs and switches, you're able to connect multiple people maybe in one area, but they can all talk to each other. Now, that's not ideal. What if I only want to talk to you? That's when things like sub-networking comes. You want to make networks within networks, and then you only have a couple of networks talk to each other. It's called segmentation, right? Mathematically, segmentation is also a simple concept. It's applied here as well, right? So that's when you create networks within networks called sub-networks, right? Mathematics really helps you, and we'll look at it, why. Okay. I can't talk about computer networking without talking about the 7 layers of OSI model, right? You can obviously Google this, and I actually took this picture from Wikipedia, and in a general level, when two computers talk to each other, regardless of where they are, they technically go through 7 layers, or at least according to the International Standards of Organization that's standardized on this, right? Computer networking is governed by a lot of standards, a lot of protocols. Just like mathematics, right? There are some fundamental truth. There are some things called rules, protocols, and you have to follow them. If you don't follow them, you don't make sense, right? So just like mathematics and the computer networking, there's a lot of protocols, standards, rules, and regulations. You do them right, then there are no issues, no concerns, right? A lot of these standards and protocols are written by various standard bodies in documents that is called Request for Comment Documents, RFC. You can look that up as well. Many of the things I talk here, they all have an RFC document tied to it, right? So let's take an example of two computers talking to each other. I'm going to walk you through these 7 layers, and that'll hopefully tell you how this works, right? So I'm going to go top down, meaning I'm going to start at the top layer, which is layer 7, and then we'll go down to 1, because that's how technically something is created and it's sent down the layers. And then on the other side, it's broken from bottom layer up to the 7th layer, right? Okay, so let's take an example. We're doing Zoom today. I'm using an application called Zoom. So are you all, right? And we're all in this application today and across worlds, and we're able to talk to each other. So the top 3 layers, like application, presentation, session, they're all part of what's called the data layer, right? What those 3 layers help you with is they together, together they help put this application called Zoom, or even if you're web browsing, HTTPS application, any number of applications, it helps, these 3 layers helps put them all into a certain format, right? Whether you're looking at web browsing or you're sharing files, you just created this new paper on mathematics and you want to share it with somebody, you send them a file. You take that, and then a Word file is different from a Notepad file, which is different from some other kind of text file. So there's different types of character encoding that goes with all of this data. Sometimes you send zip files because your file is too big. So you're working with compression algorithms, and there's data encryption. Because you don't want somebody else to see your data, you will encrypt that data, and then so that the other side is the only one that knows how to decrypt it. So all of these things go together and form what's called the application presentation session layers, right? So we do all this, and then I am speaking to you that gets put together in a certain type of application. You add all these encodings, compression algorithms, encryption, decryption, encryption, and then you give it to the computer, and the computer now takes it on the transport layer. This is where you decide what transport layer you use. There are different types of protocols at this layer. There's TCP, there's UDP. TCP, there's a lot more chatter, right? Meaning I have to send something, you have to acknowledge, then I send you. UDP, you just send it and hope that it gets there, right? Mathematical equations in the back end help you reorder packets or not, so that packets get to the other side. Then it gets to the network. This is where we're talking about sending stuff from my computer over my internet to your computer through your internet, right? And then once it gets to your section, then you take that and you put it into your local area network, which is basically from your house router to your computer. And between us is a lot of physical layer, right? Traffic goes over my internet. There's a cable running to my router, right? Computers talk in bits. We'll look at this next. And then you take those bits and you convert them to electrical signals, or you have to convert them to light signals, infrared light. Optical fiber communication is the standard of exchanging communication across countries. There are a lot of undersea cables between here and India where my information is passing through, right? Those are your physical medium. How does a computer convert what I'm speaking down to that optical fiber is the intelligence that the physical layer has, right? That's how, in general, the 7 OSI layers model work. When the traffic gets to the other side, meaning your computer, you do things in the reverse, right? So you get an electrical signal or a light signal, and then you convert that into your data layer and then into a network packet, which then addressed with the transport, either it's TCP or UDP. Eventually it becomes your Zoom application, right? All this intelligence I put in, or my computer put into the packet, sent it across, you got that same packet. You slowly start peeling the onions, if you will, and start looking at the bottom of the packet. Then you know it's a Zoom application, and that's how you're looking at my video. That's how you're looking at my audio, right? None of this is possible without mathematics, and I can't stress that enough. And so let's go straight into that and see some of the mathematical terms and concepts that you see in computer networking, right? One of the first thing is computer bits. This is a binary concept, meaning there's only 2 values. The values are 0 or 1. This is the basic unit of data that a computer uses, digital computers use, right? So, you combine 8 bits together, it becomes a byte. And then an example of this is like an IP address. When you do in the networking layer, when computers talk to each other, they all have what's called an IP address. It's kind of like the street name on your postal letter, right? How do you know which street to send it to? You use an IP address, for example. And we talked about like the physical layer, communications, optical fiber is a mathematical field of its own. Optical fiber communication is basically where you transmit all this data, this electrical data, into light signals, right? Infrared light. There's so much invention, so many people writing PhDs and papers on all of this, so they can improve. How can you make it even more faster? It is supposed to travel at the speed of light, but obviously it cannot because there are physical limitations. People are constantly trying to overcome those limitations, make it even faster. So there's absolutely no lag even when you and I are talking over miles away, right? Or kilometers away. So optical fiber communication is a mathematical field of its own. All this goes to this computer bit, that gets traveled over the physical medium. At the data link layer, we saw this is layer 2. There's things called MAC addresses, which is basically two computers in the same physical domain. Like think of your router as a computer and your computer as a computer. Those things are usually connected by a wire. They both have a MAC address, and that's how they know how to send packets to each other, right? MAC addresses are nothing but addresses tied to the network interface card on your computer. Each computer has that, and these MAC addresses are unique. They have 48 bits, right? We talked about a bit, a binary value 0, 1. MAC addresses could have 48 bits, which means, and we look at this in a second here, bit I mentioned is binary. So you should start thinking about log base 2 tables, right? Logarithmic table of base 2. And if you think about apply that here, 2 power 48 combinations are possible. It's a pretty large number, right? That many MAC addresses are possible. There's a lot of errors that can happen in the physical layer medium, right? If you think about it, this is very complicated, connecting two worlds and making sure everything I say is exactly what you hear. There are errors that happen in the physical medium. There are mathematical equations called error checksums and things like that, that make sure that if there are errors, you can confirm them. And if able, you can correct them. So those are all mathematical equations in the back end that help you make sure that you overcome those errors. So when I say IP address, you hear IP address, right? There's security in this layer too. I won't go into those details, but let's talk about IP addressing. So I'm kind of going from layer 1, 2, 3 now, then we'll stop here and touch on a lot of the mathematical concepts around that here, right, on the network layer. I mentioned this earlier, connecting two computers, it's simple, but when you start scaling, you need to start segmenting networks. And when you start talking about networks, the first thing anyone should think about is IP address, right? IP address, I mentioned, is like that unique number that you can use to identify yourself in your network, right? Now you need, 3 types of addresses. Now this is when it gets very technical, but it's mathematically related. And hopefully I have some fun exercises. Maybe you can think with me and see if you can get it. You need 3 things called IP address, then a subnet mask, and then a default gateway. The IP address is what is kind of like your name, right? And then the subnet mask is what dictates how big your network is and what network you belong to, your local network, right? And the default gateway is the IP of your router, the default gateway IP. I mentioned this earlier. You want to send it across networks, you need something called a router. It's a very important concept. Computers in a network send your packet to the router if it needs to go to the internet or to some other network, right? That's how networking works. By breaking down networks and having this one person, in a sense, be the person that receives all the packets from its networks and has this one exit point to the internet or to other networks, right? And so IP address is how you do kind of address all of that. IPv4 version 4 address is the older version, but it's still very commonly used in computer networking. It's 32 bits. So think about 2 power 32. Only that many IP addresses are available. 192.168.0.1. This is an example of how IPv4 addresses are written, right? Then there's classful and classless IP addressing. Initially, when people started off, there's 2 power 32 addresses possible, but they divided it into certain classes, class A through E, A, B, C, D, E. But we all quickly noticed that we were running out of IP addresses. 2 power 32, even though it seems like a big number, is not enough to cover the entire world and the number of devices that's on the internet, right? My phone has an IP, my computer has an IP, my tablet has an IP. In some cases, your kitchen refrigerator might have an IP, things like that. So it's just blown out of proportion. So IPv4 addresses are going out, and so people just started doing what's called classless. They removed all the classes and said, you don't have these perfect boundaries for dividing networks. In those 2 power 32, you can divide it any which way you want, and you can assign networks any which way you want. Another solution to that was IPv6 addresses. The difference is it has 128 bits, 2 power 128. That's a very large number. So far, it hasn't completely taken over networking in computers. IPv4 is still very prevalent, simply because, think about it, 2 power 32 devices in the world already have an IPv4 address. You want to convert all of that to IPv6, it's a little hard, so it takes time. How can you apply all of this from a mathematical standpoint, right? So we just walk through computer networking, some generals. Let's talk about some applications. I just talked about networking. Subnetting with IP addresses is a major application of mathematics. This is just simple math, but with a twist, which is you need to know log base 2. If you know log base 2, if you memorized it, then you will do really well with subnetting with the questions I'm about to ask, right? Throughput calculations. What is bandwidth? What is throughput? How do you measure latency, jitter? What is all this stuff? All mathematically relevant stuff. And then when I talked about routers again, they all operate with protocols. How do you calculate the shortest path from here to there, right? All that is done by mathematical algorithms, right? Called shortest path calculations. Topology calculations, right? Using topology mapping. Mathematics in general is a pattern. I think it's about finding patterns. And topology, the study of itself, is a type of mathematical field. And it's really helpful, especially in dynamic routing scenarios in networking, right? And then security. We talked about data encryption a little bit, but if you think about cryptography, that was a perfect example of a number theory applications, right? Number theory, from what I read, supposed to be the purest form of mathematics, theoretically speaking, but even that now has real life applications. Cryptography is one of them. Diffie-Hellman algorithm is a very commonly used security protocol in networking. And then statistical equations and analysis, using that to deduce values, understand how much traffic is going in your network, and then how you can get some cost analysis. All that is based on statistics. That's a direct application of mathematics, right? And then there's a whole lot of different other things like best path calculations and things like that. Automation in general, automation is a big thing. And all that directly comes out of mathematics, right? So let's look at some of those details. I know I have another 20 minutes, I think. So we'll go into the details and then finish off. Okay, subnetting. I talked about this. This is very useful in breaking a large network down to smaller networks so you can have communication more in a hierarchical manner. How do you do that? You do it with an IP address and a subnet mask, right? For example, here's an IP address, right? It says 192.168.100.0/25. The 192.168.100.0 is the network ID. The /25 is the subnet mask. Okay. Take the /25. That translates to 255.255.255.128 in IP decimal notation. Okay, this is how in computer networking we represent IP addresses. Subnet masks, we make it easy and say /25. But if you think about IP addresses being 4 bytes, 32 bits, right? So 25 out of 32, that's what that /25 means. So if you translate that to binary, because at the end of the day, computer speaks in bits, which is binary. So you translate that to binary, this is how that looks, right? 25 ones followed by 7 zeros. The 1 represents the network bits, the 0 represents the host bits, meaning the first 25 bits of that IP address represent the network, right? Meaning that's your host network. And then the next 7 bits are the available bits to create hosts. This is where you apply your log base 2 skills. What is 2 to the power of 7? 128, right? That's how many IP hosts are possible in this network, right? So hopefully you're tracking with me so far. Just to recap, 198.168.100.0/25, there's an IP address and then the /25. That 25 translates to all of this. At the end of the day, what that represents is in 192.168.100.0 network, I can have up to 128 hosts, right? Meaning if you apply this to CNC's building, you can have 128 computers in that building and all of them will get an IP address in this network, right? Technically, it's not 128, there's 2 you have to subtract. It's only about 126, some say it's 124, but just to give you an idea, right? Now, what do you think is the last address in that network? Now, I said 192.168.100.0 is the first address. And there are 128 possible hosts. What is the last address possible? It's 192.168.100.127, right? Because you start with 0, you go up to 127. Okay, now if that's your network, what would be the very next network to that one? It would be 192.168.100.128, right? Because 192.168.100.0 to .127 is one network. 192.168.100.128 is another network. So how would you represent that? You can say 192.168.100.128/25. Okay. So 192.168.100.0/25 means it goes from 192.168.100.0 to .127. The next one is .128/25. This is how mathematics log base 2 helps computer networking today to divide networks. Without dividing networks, it is very hard to establish communication. You won't know which network you're talking to, right? You need to have proper IP addressing. You need to have proper segmentation. You need to have proper subnetworks. Mathematics in real play here for us to help divide networks and establish that communication, right? Okay, then there are things like throughput measurements. Now, before I talk about throughput, I want to talk about bandwidth. Bandwidth is the raw amount of data you can send from one place to another, right? From source to destination. Your internet provider might say, hey, you have 300 megabits, or it might say, hey, you have 1 gigabit, or it might say you only have 30 megabits. What does that mean? That means at any one time, you can send 30 megabits through your internet. That's your bandwidth. Now, over time, meaning multiple computers can send information to that same exit point. Remember, the router is that one exit point of the internet. How do you manage all that, right? And mathematics applies there as well. But over time, the amount of bandwidth you can send, now that's called throughput. This is measured in log base 10 values. So it starts as bits per second. Again, bits, computers, right? Then it's megabits per second, it's gigabits per second, it's terabits per second, it's petabits per second. Basically, each one of those is 3 log values at base of 10, meaning each one of them is 1,000 times more than the other, right? So bits per second to megabits per second is 1,000 times. So 1,000 megabits per second makes 1 gigabits per second. 1,000 gigabits per second makes 1 terabits per second. So log-based 10 mathematics in play here, right? I talked about this really quickly. There's, I think, another theory in mathematics called queuing theory. You know, what if multiple people send traffic at the same time? How do you manage all that, right? Queuing theory applies here. This is what dictates, okay, which computers packets get served first. There's multiple people coming in, multiple packets coming in, many people sending files in your computer network. How do you manage all that? You know, there's computer formulas based on mathematics that take into effect who came first. Some of them would be like, whoever came first will go out, meaning first in, first out. Or you can weight things, meaning if this is a very important packet, like voice or video, right? That should get higher priority than someone going to YouTube, right? Just browsing. So you can do those kind of things. And the router will take all that into account and send the traffic that's most important. All of this is based on mathematical queue theories, right? This is how you manage latency and jitter. Latency is just how long it takes for a data to get from one place to another in times. Not how much, but how long, right? If I speak now, it takes 1 second for my voice to get to your house. That's called latency. And the variation in latency, sometimes it's 1 second, sometimes it's 3 seconds, sometimes it's half a second. That's jitter, right? All these things are calculated using mathematics, and they're a good indication of how good a computer network is, right? So that's why these things are very important. Things like queuing theory applied to throughput measurements, bandwidth measurements, latency measurements, jitter measurements, very important to identify quality. Okay, and then taking it another step further, I mentioned this a little bit earlier, with networking, when you have routers and things and such, you really have to understand what's the shortest path between 2 endpoints. Between here and India, there's a whole bunch of networks before it gets to your end network, right? So a lot of different kinds of routers, right? My traffic comes through my my provider here called Verizon. That goes through somebody else. That goes through an undersea cable and then hits another router on that side. That gets to Kerala eventually and other places in India. And there are routers everywhere, right? But how do I find out the shortest path, right? I don't want to go the wrong way to get to a place. All that is based on mathematical formulas, right? Algorithms that you use to calculate shortest path. Some algorithms that are very well known are distance vector algorithms based on Bellman-Ford algorithms. These are applied for protocols like RIP, and then there's Dijkstra algorithm, which is based on link state algorithms. Good examples of these are OSPF, ISIS. Then there's path vector algorithms. These apply to protocols like BGP. These are all computer networking terms I'm throwing out there. If you don't understand them, it's fine. But the core concept here, like I mentioned, is mathematics is fundamental to a lot of this, right? And then at every layer, there are errors and checksums. I mentioned this earlier, and even at this layer, there's those. So mathematical calculations happen in the back end to make sure that the packet I send here is the same that you're receiving. If it's not, either you drop that packet and make me resend it, or you correct it if you can. And then I touched on cryptography and number theory and Diffie-Hellman algorithms already, so that's another application. And a little bit more fun stuff, right? Like I mentioned, and I saw this nice TEDx video by Eddie Wu. He's a mathematics teacher who I thought described mathematics really nicely. Mathematics, just like touch sense or hearing or smell, it's just another sense, like a sense of humor. It's a sense of understanding the world. Why? Because mathematics helps you make patterns out of things that's otherwise looked at as chaos, right? You look at something that's like all over the place, unless you coordinate that with patterns that look just like it, and you write up a mathematical formula to explain why it's like that, you will look at that and think it's just, you know, a random thing. But the minute you can use mathematics, you draw patterns, then suddenly there is a new way to look at this, right? And so the same thing applies to computer networking. There is structure, there is regularity. There's a lot of rules that govern everything we do, right? That's how computer networking is also very tightly related to mathematics, right? Graph theory is used to deduct topologies, short path calculations using topologies. When you talk about cloud networking, everything is in hierarchical organization. So the top person can pay for all the other organizations under them. It's all hierarchical based on patterns, right? Security flows, if you want to secure your traffic, you want to go through certain patterns, those have security patterns written all over them as well. So these tie nicely into mathematics and what fundamentally mathematics to me is, at least. So here's an example of what a pattern looks like, right? This is what AWS and Azure clouds connect to. I just threw out a couple of terms. Again, if you don't understand those, or if you already know about it, great. AWS and Azure are cloud providers. I mentioned this earlier. Future of networking is cloud computing. Anyone interested in computer networking should definitely learn about cloud computing and how networking, security, mathematics in general is important there. This is how a certain computer network could look like. I am talking about connecting multiple different networks here, right? I am able to deduce a pattern because there's a mathematical formula to this on how things connect. And I've been able to come up with a pattern based on that. Otherwise, this will just be just a bunch of dots and just things connected. I don't have a pattern, right? From here, because I have the deep cloud experience, I know what's talking to what, and it looks right and it looks great, right? Here's another one for you. So this shows traffic flow that's going per port. We talked about the OSI layer, layer 4 transport that has a port number attached to it. That's the port number I'm talking about here. And it also talks over time, which is pretty neat, right? So I'm able to look at evidential data that's going through my network because this software that's showing me this has all that mathematical calculations on the back end, and it's able to present me with this pattern. Hey, look, this is how much traffic that's gone through in your network in the last hour or so from these different types of port numbers, right? Again, mathematical analysis on the back end that enables us to get this pattern. And then there's a bunch of different protocol calculations, applications where things apply, statistics. This is one of my favorites. Just a small joke there. Have you heard of the latest stats joke? Probably, right? Statistics is not just about probability. You can use statistics to actually deduce, information and use that. I don't have to preach most of your mathematics, all of your mathematics experts. So statistics is very useful. Some of the samples I showed of pictures, all that network sampling is based on statistical analysis of data that's going through network. And I'm able to identify what my network looks like, right? What's talking to what. And I can use that information to do many things. The way Google, for example, is able to advertise to you very relevantly based on your searches, right? It's because in the back end, they're doing statistical analysis of how a user behaves on the internet, right? And they're able to deduce that, oh, you just looked at gardening, for example. So I'm going to send you all these information about gardening when you're browsing in other places. So all that is because of this mathematical statistics and equations that they draw on the back end to deduce all that. Obviously, accounting is a big deal. You can account for data that's going through a network, do all that analysis, and then provide, chargebacks. You can use to say how much network is adding value. Many times, network is that thing for some people, especially who are in the application level, or if you're just using it. Network is just something that you need. It's not something you want to know about for some of them. And this can help. It can help show how much value network is adding, right, by doing this cost analysis. And automation is another great example. Software-defined networking, orchestration, virtualized cloud infrastructure. There's a lot of things that I could throw at you guys, but basically the idea is all this innovation in technology and in computer networking has been possible because we're building on top of building blocks, fundamental languages like mathematics and physics and other languages, right? Okay, final thoughts, a little bit of free advice, take it for what it's worth. I like to think about, again, in mathematically speaking, if there's one thing I would say is think of this as a 0 to 1 strategy, where there was nothing there, and then you create something, and there's something there, right? All this information you're getting in the next 3 days, take all that information and then make something out of it, right? So that's a 0 to 1 strategy. Technology, IT, all of that can be stereotypes, but try and embrace it. I learned to love technology. I think anyone can, especially mathematics majors can fall in love with technology. It does a lot of good things. And the best way to learn technology is to try, right? Not just for the sake of trying, but just to do it, just take a mathematical formula, apply it, and see how it can work for you. So, again, I'm not a mathematics major. I love mathematics, and I try to see how it helps in the field that I'm in. Otherwise, I do hope that this has been helpful. My special interest these days, I mentioned I am a technology strategist, because I love technology. I love the fundamentals of technology and how it can help businesses and even education departments. So if you're interested to learn more about the history and try to familiarize yourself, try to see the patterns on how technologies evolved and how mathematics has helped. So hope this was helpful, and I'm going to stop sharing now.
Thank you, sir, for your insights. Dear participants, if you have any doubts or queries, please feel free to post your doubts in the chat box. Hariram, sir, we are having one of the participants asking a doubt. So this is the doubt. What is the opportunity of max graduate in the field of information technology? Should I repeat?
No, that's a great question. And my apologies. I feel bad. I did not share my screen at all. I hope someone had mentioned something, or maybe you didn't know I had a PowerPoint presentation. So before I answer the question, maybe I can send this presentation to somebody so you have it, and you can share with your users maybe. Okay. Anyway, okay. The question is there opportunity for a mathematics major in information technology? I think I just made a strong case for yes. right? I didn't specifically learn mathematics in my undergrad or postgrad, but obviously I have strong fundamental background in mathematics, and it's definitely come in very handy. I think if you have mathematics, a little bit of learning on computer networking can really be very good career path. So the answer is yes, most definitely.
So we are having another doubt. So the participant is asking, what is the opportunity of maths graduate in higher studies in places like USA?
Yeah, so the things are a little complicated right now, right? Obviously, with the current environment, the current political climate in the US, and the relationships with India and things like that. But I think for especially if you are a candidate who's like, done a lot of things in masters and maybe looking at doing PhD, coming like that is a great way to, in other words, follow the path that I did, which is to do your higher studies. That's a good path. Jobs wise, mathematics majors could get jobs in computer networking that could get you to the US. There are opportunities there, but it's a little bit harder than what I did, like specialized in computer networking and telecommunications and things like that. So it's slightly different and slightly more harder to just a mathematics major to get a technology job. You do need a little bit more real world experience or theoretical knowledge by classes around computer networking and things like that, which will make it a little bit easier. Again, I'll caveat all that by saying current political climate in the US is very different. In fact, opportunities, are great in India as well. So it's really what you want to do, but I think there are possibilities.
Thank you, sir. I think there are no more doubts. So continuing with the session. Now I request Dr. K.P. Uma, Professor and HOD, Department of Mathematics, Hindustan College of Engineering and Technology, Coimbatore, to take over the session. Ma'am, please.
Hello, can you hear me, ma? Hello,
Yes, ma'am, we can hear you.
yeah, can you hear me?
Yes, yeah. Okay.
Okay, I'll proceed now. Good morning to all. I'm immensely pleased to present. I'm immensely pleased to present in this conference on productive mathematical discourse. On this day, my topic will be focusing on mathematical models on manpower recruitment. First of all, I extend my gratitude to the management and the secretary of Christ College for having given me an opportunity to present this webinar. My sincere thanks to head of the department for inviting me as a personally let's start the mathematical models on manpower recruitment. First of all, my topic mathematical models on manpower recruitment. Actually, manpower planning is the process of systematically forecasting the future demand and supply of employees, through which management determines how the management should move from its current manpower to its desired manpower utilization. Further, human behavior is highly variable, and it is therefore essential to model manpower planning that accommodate population heterogeneity. Today, my program focuses on the construction of different mathematical models for recruitment with a single and two-grade manpower system, incorporating either univariate policy or bivariate policy using shock model approach. Again, for the constructed models, the performance measures can be namely expected time and the variance of time to recruitment
Ma'am,
or
sorry.
derived.
Hello, ma'am. Sorry for the
Hello.
interruption. Ma'am,
Okay, sir.
ma'am, your video is stuck and we cannot see your. Is any presentation? Are you doing any presentation now?
Yeah. PPT
Ma'am,
and
PPT is not
couldn't
visible.
see. Okay, sir. Wait. I'll come. Yes. Now you could see my
Yeah,
PPT.
it's
Thank
fine.
you. Thank you.
Okay, ma'am.
Okay, let me start once again. My topic is mathematical models on manpower recruitment. Manpower planning or recruitment is the process of systematically forecasting the future demand and supply of employees, through which management determines how the management should move from manpower to its desired manpower utilization. So further, human behavior is highly variable, and it is therefore essential to model manpower planning that accommodate population heterogeneity. Today's program focuses on the construction of different mathematical models for recruitment with single and two grade manpower systems, incorporating either univariate or bivariate policy using shock model approach. Further, for the constructed models, the performance measures, namely expected time and the variance of time to recruitment, are derived, and even the numerical illustrations are added to highlight the performance of various models. Let us see what is that explanation of manpower planning. Manpower planning is an attempt to manage the supply of people with jobs available for them. It is viewed as a process by which management determines how the organization should move from its current manpower structure to desired one. It depends not only on the highly unpredictable behavior of human beings, but also on the uncertain environment of the organization. So this uncertainty leads to propose a stochastic models on manpower planning. These models incorporate several factors such as recruitment, training, promotion, demotion, and even wastages. So these factors are interlinked and their analysis become highly essential in order to analyze the cost involved in recruitment. So manpower planning selects the optimal number of human resources and the correct type of employment available for them at right place and at the right time. So through manpower planning, the management of any organization optimizes the expertise and the skills of human resources at minimum cost. As a definition by Colima, it is given as the process of determining manpower requirements and the means for meeting those requirements in order to carry out the integrated plan of organization. Actually, in administration as well as the production oriented organization, it is an usual phenomena that decision personal whenever the policy decision regarding revision of wages, incentive, and the revised targets for sales are announced, which in turn lead to depletion of manpower, which can be capitalized in terms of man hours. As recruitment involves several costs, it is usual that organizations have natural reluctance to go in for frequent recruitments, and hence suitable recruitment planning has to be designed in order to offset the loss of manpower. So the recruitment planning is very much essential because the recruitment involves the cost. So the planning should be very carefully done. The main dimension of the manpower planning should be the total number of employees presently available and their types, nature of work, wages, etc. And even it should be a detailed description for each position of employee working in different departments should be identified, and even age distribution, qualifications, experience of the employees that also to be considered into account. The main objective of that manpower recruitment should be to make available the human resource in adequate quantity and of required quality. And also it should reduce recruiting and also replacement cost to reduce labor cost associated with attrition. And also it should be aimed to estimation of short term, long term, and also medium term manpower needs. The manpower estimation can help an organization to retain the desired employees longer and keep them functioning more efficiently and more productively at a reasonable cost. Then let us see, is it necessary to need for the planning of this manpower, that is before going for recruitment? Yes, let us see certain points on this. Why do you want to go for manpower planning means the shortages and surpluses can be identified through manpower planning, and also all the recruitment and the selection programs are based on manpower planning only. Then only it will be effective. And also it is necessary to reduce the labor cost as excess staff can be identified and therefore overstaffing can be avoided. And it is necessary to identify the available talents in the concern, and accordingly training programs can be chalked out to develop those talents. Even growth and diversification of business, and also through manpower planning, human resources can be available and utilized in a best manner. And it implies the importance of manpower management, which ultimately helps in the stability of a concern. Actually, the recruitment means any organization is merely a blueprint for human activity, and it requires people in order to function. The mere passage of time causes some people to grow or to retire or to die or to become an incapable. So both seasonal and cyclical fluctuations in business cause a constant ebb and follow in their force. Hence, employees constantly need to be replaced. So before going for this recruitment, we need some basic concepts and the definitions which are used in the construction of mathematical models of manpower planning, and they are given as the first and foremost is wastage. Wastage arises due to an act of individual leaving the system over which an organization cannot have any control, and also it depends upon the personal and environmental factors. The wastages can be voluntary or involuntary. In an organization, voluntary wastage happens due to, we can say withdrawal of a person from the existing job, and also as an involuntary wastage, we can have it as a due to death, ill health, retirement, and also redundancy. It can be successful for any organization if and only if it is possible to predict the pattern of wastage. If the total number of persons is fixed, wastage creates vacancies, and so promotion and the recruitment opportunity arise. Manpower planning can be made successfully if and only if it is possible to predict the pattern of wastage in the organization. If the pattern of wastage is evaluated, then the necessary number of promotions and the recruitments can be decided. And also through the study of wastage only, one can decide the health rate of organization, the level of absenteeism, and also the industrial dispute. So on the whole, we can decide about the organization stability only based on wastage rate. Next, we'll see some policies of recruitment, that is control limit policy. Let us see what is the control limit policy. So it is one of the it is used in the recruitment. A recruitment policy in which it is made, recruitment is made upon satisfaction of some conditions such as accumulated loss of man hours exceeding a certain fixed value, or maximum loss of man hours crossing a pre-assigned constant, or the number of decisions reaching a certain fixed number, and hence like this we can add the number of policies limitations. Next comes the counting process. Actually, stochastic process, we all know that random variable with the time considered as a stochastic process. One among that is counting process. We'll have a clear idea about counting process, which will be used for recruiting the manpower model. So the counting process is actually a stochastic process, say n of t, with a time greater than or equal to 0, is said to be a counting process if n of t represents the number of occurrences of an event up to a time t, where the conditions to be satisfied are all this n of t should be greater than or equal to 0, and it is an integer valued, and also whenever s less than t, n of s should also less than n of t, and the difference n of t minus n of s equals the number of occurrences of an event during the interval of a time s comma t. So that is counting process. Next comes Poisson process. The counting process n of t. So now we are counting the count n of t as a counting process. It is said to be Poisson process under lambda greater than 0 if that n of 0 equal to 0, and also the process has strictness and independent increments as probability of h equal to h plus order of h. So probability of h greater than or equal to 2 means it will be considered as a finite decimal length h, and that order only p of n of greater than or equal to 2. Next comes the renewal process. See, consider the sequence of non-negative, independent, and identically distributed continuous random variable. Let us have xn with a distribution function, say capital F, and let s not equal to 0, and Sn is sum of n terms x1 plus x2 etc. up to xn, where n greater than or equal to 1. Then Fn of x is probability of Sn less than or equal to x, and n of t equal to supremum of all those n with Sn less than or equal to 1. This we call it as a renewal process. Next comes a geometric process. Sometimes the recruitment models can be obtained by considering this geometric process. The geometric process, if there exists a real number, say a, which is greater than 0, and the set of all ai minus 1 into xi, where I varies from 1 to etc., this forms a renewal process. Then we say it is as xi is called it as a geometric process. As a particular case, the geometric process is decreasing if a is greater than or equal to 1, and it is increasing if a lies between 0 and 1. And if you see that when a equal to 1, what will happen means, then it is a geometric process reduces to renewal process. When a equal to 1 means this reduces to renewal process. Next, we are going to use the model approach. In what approach we are going to follow this, construct these models, recruitment models, we'll see. That is shock models and also cumulative damage process. Actually, the shock models deals with the life distribution of devices or components which are subjected to shock. That is, at every shock, a random amount of damage is caused to the device, and the damages in successive shocks can be added in the form of a cumulative damage, that we call it as a cumulative damage due to certain shocks. Next comes the survival time. In the recruitment, we are going to find out the survival time of a function only. Then only we are going to construct the model. So the first and foremost is finding the survival time, which is a very important point of this construction of mathematical model on recruitment. Yes, what is that survival time? We'll see. That is, in manpower planning, the survival time of the organization refers to the length of an interval between two consecutive decision points. The decision points may be shocks, say, in which threshold crossing is not taking place. The threshold is nothing but the constant or the variable. It is fixed by the organization. If the total number of loss of manpower exceeds this threshold, then we have to move for a recruitment. So this is another important term for in this construction of a model, threshold. And during the survival time, recruitment is not done. Yes. Next comes some distributions. Let us see that distributions we are going to see. Discrete distribution, we can have it as a geometric distribution, and this distribution, geometric distribution, is P of x equal to r equal to theta into theta, that is P theta into theta bar of r, which is a complement. Theta bar means complement of theta. And this is said to be a geometric random variable with a parameter theta, and of course theta bar is 1 minus theta. And if the geometric random variable takes the values 1, 2, 3, then it's the corresponding probability may be considered as P of r equal to P of x equal to r is theta into theta bar of r minus 1 when r equal to 1, 2, 3. When it takes the values 1, 2, 3, when it takes the value 0, 1, 2, 3, it will be theta into theta bar r. Next comes in a continuous distribution. These distributions we are going to use that is exponential distribution. Exponential distribution of a random variable, we know all that it is given by 1 minus e power minus lambda x, where x lying between 0 to infinity and lambda greater than 0, and its expected value is 1 minus 1 by lambda, where lambda is the parameter. And after that, on simplification, we are going to use the law of probability. What is the law of total probability? For a discrete distribution, it will be P of x less than or equal to x is summation over n equal to 0 to infinity P of x less than or equal to x given y equal to n into P of y equal to 1. In the case of continuous, instead of summation, we'll have, of course, the integration P of x less than or equal to x is 0 to infinity of P of x less than or equal to x conditioned by y less than or equal to y into the density function of y. X. Another distribution we are going to use is exponential distribution. The exponential distribution of a random variable with a scale parameter lambda and the shape parameter x. Alpha. Here the shape parameter we are considering as alpha will be f of x comma alpha comma lambda equal to 1 minus e power minus lambda x the whole power alpha, where x and alpha lambda all are positive always. When in the case of alpha equal to 1, it reduces to exponential distribution, and the correspond for this exponential distribution, the corresponding expected value also given as this form e of x. Just look at that e of x as a note I have given. Yes, another distribution we are going to use is setting the clock back to 0 property. What is that? We'll see. A family of life distribution with a survival function, say s of x comma beta, and it is said to have a property of setting the clock back to 0 if it satisfies the conditions that x naught is greater than 0 and the survival function satisfies the condition that s of x plus x naught comma beta under the condition s of x naught equal to beta will be s of x comma beta dash, where that beta dash is beta of x naught comma beta. Yes. So we have seen so far what are the concepts, what are the distributions we are going to use for the construction of mathematical models. Now we'll see what are the different policies are available to find out or to construct the main models for time to recruitment. So as far as the recruitment policies are concerned, it is mainly divided into two parts. One is CUM policy, the other one is a max policy. In the case of CUM policy, what you are going to do means the recruitment is done with a condition that it is conditions that total number of loss of manpower exceeds a present value. Total number of manpower exceeds a certain value, then we have to go for a CUM policy. So that may be considered divided into two parts. One is a univariate, the other one is a bivariate policy. What is univariate policy means? Univariate policy is one of the recruitment policies in which recruitment is made by considering only one of the control limit policies. Either it may be in the number cumulative loss of manpower, otherwise the number of decisions. Either cumulative loss of manpower or the number of decisions or the maximum number of loss of manpower reaches a certain point. This may be univariate. One of the recruitment policies alone we are going to consider in the case of univariate CUM policy. In the case of bivariate CUM policy, two concepts we are going to see. That is, the recruitment is made by considering two of the control limit policies. Suppose if it is a cumulative policy, bivariate CUM policy means the recruitment is made whenever cumulative loss of manpower exceeds the threshold or the number of decisions reaches a pre-assigned integers. Number of decisions reaches a pre-assigned integer n. Whichever occurs earlier, we go for bivariate CUM policy. And even in the same thing for max policy. Max policy in commonly it is used that it is a policy recruitment is made whenever the maximum loss of manpower exceeds a positive constant. And here also you have univariate and also bivariate max policies. Yes, what are the methodology we are going to do? Our main aim is to find out the time to recruitment. In that, we are going to use the loss of manpower, interdecision times, and the threshold, and also order statistics. That may be order statistics. So this is the methodology we are going to see. Yes, now we focus on finding out this for a single grade system with a univariate policy of a recruitment. We are trying to find out their mean time to recruitment. Further, I will explain the description of this model. I am going to consider a single grade organization, and also univariate policy of recruitment is going to apply, and the survival time is considered as a geometric process, and it is also independent of process of loss of manpower. Yes, what are the notations we are going to use means, first one is Sn, survival time after n minus 1th term, and the loss of manpower, Xn equal to the loss of manpower at nth decision. Tn is the cumulative loss of manpower in the first n decision. T is a continuous random variable representing threshold value of the given policy. F distribution of T, K distribution of Sn with mean A greater than 1, and G distribution of Xn, Gn is distribution of Tn, that is a cumulative loss of manpower in the first n decisions. Yes, we'll see here the time to recruitment. How we are going to do that, we'll see. See, look at here. In this model, I am considering S1. S1 is survival time after the first decision. And S2. S2 is the survival time at the nth decision, second decision. And here W, I am going to consider this. The assumption the recruitment is made whenever the cumulative loss of manpower exceeds the threshold I told. So according to that, the time to recruitment, say W, will be S1 if T1 is greater than T. What is the T means? The total loss of manpower at the first decision. That yellow shade gives the manpower at the first decision. So due to first decision, there will be some loss of manpower. So that is added. And if that is considered as T1. If the T1 is greater than T, here the T is a threshold value that is fixed by the organization. So once the total loss of manpower exceeds the threshold value, we have to go for a recruitment. So W will be equal to S1 if T1 is greater than T. That is the total loss of manpower due to first decision T1 exceeds the threshold T, then we have to go for recruitment. So at that time W equal to S1, survival time S1. Next comes the second. After the second decision, look at that yellow arrow, that is second decision is announced. So at the time we'll be finding out the total loss of manpower, and that is considered as T2. And if the T2 is greater than T, and also T1 is less than or equal to T, then W equal to S1 plus S2. So it moves on W equal to S1 plus S2 plus S3 if T lies between T2 and T3. So this goes on like that. So mathematically, how could you write the time to recruitment means W equal to summation over I equal to 0 to infinity, J equal to 0 to I, Sj plus 1, chi of Ti less than or equal to T less than Ti plus 1. So we got this, and here we are applying, the chi is a characteristic function. We are applying the total law of probability, and hence we get the E of W value. E of W equal to taking expectation, and after taking the total of probability, it reduced to some double summation lambda by a power j triple integral dfu dges and dgit, and also the total cost is given by t of c equal to this. So look at the equation, and e of tc is given in the last equation after applying the total of probability. Yes, with the threshold distribution, then we are going to give the particular distributions for the given random variable threshold, and then loss of manpower, etc. So on assumption that it is an exponential distribution, E of W is reduced to this equation. The last line, you just see that lambda A into sigma 1 plus sigma 2 by A into sigma 1 plus sigma 2 minus sigma 1. Yes, and E of TC also, after the distribution, exponential distribution, it is reduced to, look at the last line, r plus 2a plus b into sigma 1 plus sigma 2 by sigma 1 into sigma 2. And I told we can also apply the SCBZ property. So on applying the SCBZ property on the simplification, this SCBZ density function only given a small f of u. Look at that equation, small f of u, where p and q are also I have mentioned here. So on applying this SCBZ property, E of W, this becomes, look at here, the last line. So that simplified form only I have given E of W, and this E of TC. This is a simplified form of E of TC when threshold is a SCB is a property. Yes, this is the equation. Yes, effect of survival. So it is not only that just constructing the model, it is not enough. We have to justify, we have to give our justification as far as this model is constructed. Constructed model should be justified, is it not? So the numerical illustrations are given. Effect of survival time on performance measures by fixing lambda equal to 2, a equal to 2, r equal to 500, a 20 and b 15, the cost values. So when t exponential and t SCBZ, we have the different values. So when lambda increases, look at here, I am increasing the lambda and finding out the expected time to recruitment and long run average cost per unit time. When the expected time to recruitment, when lambda increases, the time to recruitment is also increasing. So once it increases, if you increase the time to recruitment, the cost will be reduced. That should be our aim. Yes, when lambda increases, the expected time to recruitment is increases, and hence the long run average cost per unit time will be decreases. Similarly, when T is SCBZ also, I have found out the expected time to recruitment. Here the time to recruitment increases and the long run average cost per unit time is this is decreasing. So it is more realistic when comparatively, it is more realistic that to note that if the threshold distribution has SCBZ property, the expected time to recruitment is higher and the long run average cost is lower when compared with exponential threshold distribution, and it will be more useful for the organization also. Similar effect also I have given for sigma 1. Yes. Next comes bivariate policy. The previous one is a univariate policy. The same thing for a single grade manpower system with a bivariate policy of recruitment with a slide with a model same description. I have constructed another model, time to recruitment W, with the same conditions, but considering two control policies. One is the total loss of manpower. Here the recruitment is done whenever the cumulative loss of manpower exceeds the threshold, or the total number of decision, another condition, and number of decision reaches a pre-assigned value, say number n. Whichever occurs earlier, we go for recruitment. So that is bivariate policy. So under that condition, we got W as the equation, first equation, and the expected time to recruitment is given in the last line. The total cost is also given like this. And the mean time, of course, we are finding out the mean time when the threshold is exponential, E of W is given. The simplified form is given in the last line, in the case of bivariate policy. And also the expected total cost, and applying the conditions, total of probability, and the different distributions are applied, we got E of TC like this on simplification. Then E of W, when SEBZ property is applied, this is SEBZ property applied, and this is E of TC when SEBZ is applied. So this is the equation when SEBZ is applied, what is E of TC. Yes, the numerical illustration also, by changing the one of the values sigma 1, 1 to etc. 0.1 to 1, the time to recruitment and long run average cost. In the case of T exponential and T is SEBZ, that is threshold is exponential and threshold is SEBZ. We have found out the numerical illustration. Here also the time to recruitment increases, so the total cost is decreasing. In both the cases, comparatively, we have seen. And comparatively, we can also see that the SEBZ property time to recruitment is prolonged when you use SEBZ property, which will be useful. And not only this is, so far what we have done is application of geometric process. Not only that method for finding the recruitment policy, there are another method. This is the steps we are following for finding out the manpower recruitment using the cumulative damage processes and also shock model approach of reliability theory. First one is tail distribution. We have to find out the tail distribution of time to recruitment. Next one, distribution function of time to recruitment, then taking Laplace transform, then finding out the mean and the variance using Laplace transform. Hence, next step will be numerical illustrations and findings. So for that, I have consider one organization, a single grade manpower system with the interdecision sign as an order statistics. So these are the assumptions I have made. Decision at random oppose in 0 infinity. Loss of manpower process forms a sequence of IID random variables, and by cumulative loss of manpower crosses the threshold, or the number of decision crosses, that is bivariate I have considered. Wastage of manpower is linear and cumulative. Interdecision time is an order statistics, and the loss of manpower process and the process of interdecision are statistically independent. And look at the notations I'm going to use this. So these are the notations I have used to construct this model. Yes, using that model, we have constructed the main result, that is the survival function. This is in P of T greater than T is the time to recruitment. Here I mentioned here, and small t is the threshold value. So P of T greater than T equal to summation over k equal to 0 to t minus 1, probability that exactly k decisions are taken in this, and the cumulative loss of manpower does not cross the threshold level. That means this is the survival time. P of t greater than t is nothing but the survival time, and we all know that order statistics, the density function is given in this form. Look at the equations given and applied all the values here. Main result we have derived. When y is an exponential with a maximum m, we got E of t as this equation. Look at that. I'm not reading the equation, but we have derived that equation after simplification, and then g bar of mu equal to having the parameter lambda by lambda plus mu. And when it follows an exponential distribution with a scale parameter m and shape parameter 2, in this case, the distribution is given as 1 minus f of maximum of that whole power minus 2, and that equation is P of t greater than t is given in this form. And hence the Laplace transform, I told no, after the survival function, Laplace transform is taken. So after taking the Laplace transform, the equation reduced to the last line. Yes. Therefore, the expected time to is given from this equation. And also not only a continuous random variable, we can have it as discrete random variable. Say here xi's are given as a Poisson with lambda and y is a geometric with mu I have taken, and hence the proper PDF of t is reduced to this form. First line is reduced to equation this, then taking Laplace transform where the conditions are given, and E of t is also mentioned in the last line. Numerical illustrations, if you see the effect of lambda and theta on the expected time to recruitment. Just look at that. Lambda is increasing, theta is fixed in the first box. And the case 1 and the case 2, and then E of t is increasing, and in the case of second 2, E of t is also increasing. And in the by fixing lambda and increasing theta. First one, sorry, first one by fixing theta and increasing lambda, we got the result. The second by fixing lambda and increasing theta, we got the result. These numerical illustrations are found out by using the MATLAB. And after MATLAB and after constructing the model using MATLAB, we have constructed these models, these illustrations, and we have justified our model. And so we have seen that table 1 increases, the lambda increases, mean time for theta also, recruitment increases, and the recruitment decreases by keeping the other parameters fixed. And the assumptions will be the other cases. What are the other possible cases we can consider will be, see, as a model 1 I have given come policy of recruitment, and in model 2 maximum policy of recruitment. That is, these are the possibilities of getting the recruitment, because it depends upon the organization. We cannot focus on only one univariate or the maximum policy or like that. So we have to focus on all sorts of possibilities. So that is why in a tabular column, what are the possibilities of manpower recruitment I have given. Model and the loss of manpower, optional threshold, and also mandatory threshold also we can have. The threshold can be optional and also as a mandatory threshold. So at last we are going to find out the mean and the variance of time to recruitment only, but considering the different distributions for loss of manpower, say exponential, Poisson, and geometric, and also optional threshold may be exponential, SCBZ, and geometric constant. You can have it as a constant also. Even the mandatory threshold is maybe exponential, SCBZ, and also geometry, and it may also be a constant. These are the different assumptions we can make, and it depends upon the organization and it depends upon the models we can construct with the assumptions given like that. Look at the assumptions. Single grade organization taking decision in a random epochs in 0, infinity, and of course at every decision making epoch a random number of persons quit the organization. Also there is an associated loss of manpower if a person quits, and then there's a loss of manpower at any decision forms a sequence of independent identically distributed random variable. Sometimes we can have it as a it may be a correlated also. Interdecision times are also here considered as independent manpower.
Hello, ma'am. Is it audible? Sorry for the interruption. I think there is some network issues. So please stay tuned.
Dear participants, sorry for the interruption. We are trying our best to rectify the problem.
Hello, ma'am. Your audio is muted. Ma'am, please unmute yourself. Hello, ma'am. You are not audible. Ma'am, hello.
Hello. Am I audible now?
Yes, ma'am. Yes, ma'am.
Can you see the slide?
No, ma'am. Actually, your mobile screen is visible on the screen.
Now I think.
Now
Now
it's
I
okay.
think.
Now it's okay.
Yeah. That's right. Okay. And what are the random variables we are using? And the notations we are using here is xi loss of manpower due to ith decision, y optional threshold, z mandatory threshold, and uk the interdecision times between k minus 1th and kth decision, and t is time for recruitment. So under the case, the survival function of t is given in equation number 1. And on simplification, the survival function is reduced to, see the third equation, fourth equation, the density function, and then taking Laplace transform of density function, we have got the result as 6, equation number 6. And hence the time to recruitment under the condition that x, y, z all are exponential distribution respectively with mu1, alpha 1 and beta 1 parameters. So the second central moment, that is E of t square, found out from E of t and E of t square. Of course, we can find out the variance by using the formula E of t square, variance of t equal to E of t square minus E of t the whole square, and the numerical illustrations are given here. Just look at that lambda and mu1 and fixing that lambda 0.12, 0.25. We found out the mean and also the variance. And also we have seen that from the table, as lambda alone increases, the average interdecision time decreases. Hence, mean and the variance of time to recruitment decrease, which is more realistic. And also when mu alone increases, average loss of manpower decreases, and hence the mean and the variance of time to recruitment increases. And in the second cases, we have two performance univariate max policy is applied, and I told no univariate max policy and committee policy, all such possibilities are there. Here univariate max policy is applied, and we got the same survival function, and then L of t, and hence expected time to recruitment in equation 2, and the variance of time to recruitment in equation 3. And this numerical illustration also justified. Yes, of course, it is very, very essential to plan carefully for the recruitment. It is not an easy job also. So we have to plan very much all those considerations. What are the things consider is only a small things. The constraints are more. So to proper planning is very essential for the recruitment. So this concludes my topic. I once again thank you for inviting me as a resource personnel. Thank you one and all. If you have any queries, now I will move on to the queries section. Thank you, sir.
Thank you, ma'am, for your words of wisdom. Ma'am, what is the research scope in manpower empowerment, ma'am?
Manpower resource scopes. See, I have considered only the two constraints. Is it not? That is in the cumulative loss of manpower I have considered, and the number of decisions. These two constraints alone I have considered. And there are so many constraints that depends upon the organization, and even there are 3-grade system, and also we can move for single grade only. I consider you can go for 2-grade and 3-grade, almost 3-graded system with the different conditions they are started. And also the threshold for the distribution may be voluntary and involuntary retention. All this will be considered. So many sources are there for the research as far as manpower recruitment is concerned.
Thank
Hello.
you, ma'am.
Hmm.
If you have any queries or doubts, please post your doubts in the chat box. I guess there are no more doubts, so we can move on to the next session. Now I invite Shweta Naik, research scholar, Bangalore University, to present a paper.
Hello.
You are audible.
Yeah. Audible? Hello? Hello?
Yes, you are audible. You are audible.
Okay. Hi, everyone. Good morning. Myself, Shweta Naik. I am from Department of Mathematics, Bangalore University. And today I am going to present you that paper. That paper title is KMU Manifold Admitting Shorten-Van Kempen Connection. I start with introduction. A manifold is a topological space that resembles Euclidean space near each point. A smooth manifold M with a Riemannian matrix is called Riemannian manifold. A contact manifold is a smooth manifold M of the odd dimensional 2n plus 1, which is equipped with a differential 1 form eta that is non-degenerate in the sense that the wedge product eta wedge d eta raised to n does not vanish. The cone circular curvature tensor is the most important 1-3 type of curvature tensor from the Riemannian point of view. An interesting invariant of cone circular transformation is the cone circular curvature tensor C and is defined by C of xyz is equal to R of xyz minus R divided by 2n into 2n plus 1 into G of yzx minus G of xzy, where xyz belongs to Tm and R is scalar curvature. The short-term Van Kempen connection have been introduced in the third decade of last century for the study of non-holomorphic manifolds. In our reference, D.E. Blair and the other authors started study of cone circular curvature tensor of contact metric manifold. The main result of this paper is 2n plus 1 dimensional NK manifold is satisfying C of xi x dot C is equal to 0 if and only if M is locally isometric to the sphere S of 2n plus 1 of 1. And other author, Mukut and others continued the same work and classified KMU manifold with cone circular curvature tensor C satisfying the same condition C of xi x dot S is equal to 0. And UCD and others are studied xi cone circularly flat and pi cone circularly flat on NK contact metric manifold with respect to Levi-Civita connection. I'm motivated by all this work, and I started this characteristic condition, and that conditions are like this: zicone circularly flat, picone circularly symmetric, and picone circularly flat, pseudocone circularly flat, and partially Ricci pseudosymmetric on K-mu manifold with respect to shorten Van Kampen connection. And also we proved that K-mu manifold is locally concircularly pi symmetric with respect to shorten Van Kampen connection del bar, if and only if it is so with respect to Levi-Civita connection del. Finally, we studied K-mu manifold satisfying C dot R is equal to 0. And this is the next is the definition of K-mu manifold and shorten Van Kampen connection. A 2n plus 1 dimensional differential manifold M2n plus 1 is a contact manifold if it is carries global differential 1 form eta, such that eta wedge product d eta raised to n is not equal to 0 everywhere on M2n plus 1. This one form eta is called a contact form of M2n plus 1. A Riemannian manifold G is said to be associated with a contact manifold if there exists one tensor field pi and contravariant global vector field xi, and xi is called as the characteristic vector field of the manifold. And this contact manifold is satisfying all 3 1 2 3 4 conditions. And this fifth to 8th condition holds for K-mu manifold. And others continue by continuing the equation 9 10 up to 15 are all satisfied for K-mu manifold, as you seen in my screen. And said Schouten Van Kampen connection del bar of contact metric manifold M is defined by del bar of x is equal to del of xy minus eta of y into del x of xi minus del x eta of y into xi. And by applying these conditions, 16th equation number 16th on K-mu manifold, I got this Riemannian curvature tensor on M with respect to shorten Van Kampen connection, and is defined by R bar of xyz is equal to del bar x del bar yz minus del bar y del bar xz minus del bar of Lie bracket xy z. By using this 19th equation number 19, I found the Riemannian curvature tensor for K-mu manifold. That is R bar of xyz is equal to that equation number 20, R of xyz minus kappa into g of xyz eta of y minus g of yz eta of x into xi plus eta of y eta of zx minus eta of x eta of zy minus mu into g of hxz eta of y minus g of hyz eta of x xi plus eta of y eta of z hx minus eta of x eta of z hy minus g of pi x plus pi hx z into pi y plus pi hy plus g of pi y plus pi hy z into pi x plus pi hx. And by contracting this equation 20, I got Ricci curvature equation, that is S bar of yz is equal to S of yz plus 2k g of yz minus 2nk plus 2k eta of y eta of z plus mu into g of hyz. Again, I contracting the equation 21, and I got this scalar curvature equation, and that equation is R bar is equal to R plus 2nk. With respect to with respect to shorten Van Kampen connection, I got some equations, and that is as you can see in screen, that is 23, 24, 25, 26 equations. Next, I move on to my results. Firstly, I consider zicone circularly flat condition, and that definition of zicone circularly flat is given by a differential manifold M satisfying the condition C bar of xyz is equal to 0 is called zicone circularly flat. And I doing some calculations, and I got this results, and that result is in terms of eta Einstein manifold and I got the expression for scalar curvature with respect to Lewis-Vita connection by equation number 29. I state the theorem, and that theorem is let M be Xi-concircularly flat manifold admitting Schouten Van Kempen connection. Then either M is eta Einstein manifold or R is equal to minus 2nk with respect to Lewis-Vita connection. Next, second condition is pi concircularly semisymmetric, and the definition is given by a differential manifold M satisfying the condition C bar of xy dot pi of z is equal to 0 is called pi concircularly semisymmetric. By the definition, I got this equation 30 and doing some calculations, and I got this equation number 34, and by equation number 34 I state the following theorem that M be pi concircularly semisymmetric manifold admitting Schouten Van Kempen connection, then either M is eta Einstein manifold or R is equal to minus 2nk. And next condition is pi concircularly flat, a differential manifold M satisfying the condition C bar of pi x, pi y, pi z is equal to 0 is called pi concircularly flat. And doing the same calculations, I got this equation number 38, and therefore I state the following theorem that M be pi concircularly flat manifold admitting Schouten Van Kempen connection, then the scalar curvature R is equal to 2nk into 4n square plus 3 divided by 4n square plus 1. Next is pseudo-concircularly flat. Definition is given by a differential manifold M satisfying the condition C bar of pi x y z is equal to 0 is called pseudo-concircularly flat. And by using definitions and some calculations, I got this result. That result is equation number 42. By that, using that 42, I state the following. Let M be pseudo-concircularly flat K-mu manifold admitting Schouten Van Kempen connection is eta Einstein manifold for Sasakian case with respect to Lewis-Vita connection. Next is I move on next definition, and the definition is partially Ricci pseudosymmetric, and the definition is given by a differential manifold M satisfying the condition R bar of xy dot S bar of UV is equal to F of P cube bar of G of S bar of xy UV is called partially Ricci pseudosymmetric, and where q bar of G S bar of xy UV is equal to X wedge product with respect to G Y C S bar of UV. By using definition and some calculations, by doing some calculation, I got this equation number 47, and that is S of YV is equal to some constant into G of YV and plus some constant into eta of Y into eta of V. Therefore, I state the following theorem that M be partially a Ricci pseudosymmetric K-mu manifold with respect to SVK connection, then M is an eta Einstein manifold provided F of P is not equal to 0. My next condition is locally concircular pi symmetric, and definition is given by a 2n plus 1 dimensional K-mu manifold is said to be locally concircular pi symmetric with respect to Schouten Van Kempen connection if pi square of del W of C bar of XYZ is equal to 0 for all vector field XYZW orthogonal to vector field Xi. By taking covariant derivative of C of XYZ, I got equation number 49, and doing and taking pi square on both sides, I got this equation number 50. And lastly, finally, I got equation number 51, which states that K-mu manifold is locally concircular pi symmetric with respect to Schouten Van Kempen connection del bar if and only if it is locally concircular pi symmetric with respect to Lewis-Vita connection del. And finally, I considering one condition, and that condition is C bar of xi x dot R bar of yzw is equal to 0, and doing same calculations as you can see on my screen. I got last equation, that is equation number 57 as my result. And I state the following theorem, that M be 2n plus 1 dimensional K-mu manifold satisfying C bar of xi x dot R is equal to 0 with respect to shorten Van Kempfen connection. Then M is an eta Einstein manifold. And these are the reference that I gone through. Suggestions. Thank you. Thank you. Hello. Hello. Can anybody hear me?
Yes, ma'am. Your voice audible. Thank you.
Thank you.
Bhavani, over to you, Bhavani.
Thank you, ma'am. Last but not the least, I humbly call upon Mr. Rajesh Kumar R, Assistant Professor, Department of Mathematics, Nagar College, to deliver the vote of thanks. Sir, please.
Thank you, Bhavani. Good afternoon, all. Respected Principal Dr. Jolly Jacob, my father Dr. Tito Varghese, CMI, Head of the Department Dr. Mary Matilda Rose. Thank you. Today, I am proudly honored and deeply humbled by that the Department of Mathematics, in association with Kerala Mathematical Association, organized the 3-day international conference on productive mathematical discourse. Okay, well, the day one ended up in grand success. Okay, on behalf of the Department of Mathematics, Nagar College, I take this opportunity to extend my sincere gratitude to our respected dignitaries and delegates who joined all across the country. And first of all, I take this opportunity and I would like to express my sincere thanks to Dr. Sunny Kuriakos, the Secretary, Kerala Mathematical Association, with his guidance and support, which made us able to host this international conference. Thank you, sir. Thank you very much, sir. Today, we are privileged to have an opportunity to listen Mr. Hariram, Cloud Solutions, Marvel Studio, California, USA. I extending my sincere gratitude for gracing this program through his wonderful talk and on an initiation of mathematics into technology. Thanks a lot, Hari Ram, sir. Thank you very much, sir. I extending my sincere gratitude to Dr. KP Uma, the professor and the head of the Department of Mathematics, Hindustan College of Engineering and Technology, Coimbatore, for gracing this program with a talk on mathematical model on manpower recruitment. Thank you, ma'am, for a wonderful session. Thank you all, and all the participants are waited for all this through this time and joy and still stay tuned with us for until the end of this session. And I extending my sincere thanks and to the participants, those who are joined with us on the day one of the international conference today. And we are expecting the same kind of participation in coming days. So thank you, everybody. Thank you very much. Thanks a lot.
Thank you, sir. With this, we have come to the end of today's session. Once again, thank you all.
and the feedbacks form will give only after the completion of our international webinar, and we have to wait until Wednesday. So we are expecting your participation in coming days also. Thank you very much. Thank you all.